Hello. So this is the demo for probability fundamentals for deep learning. So we'll start with the basics. What is probability and why it is needed. So probability is uh, uh, chances of having of having anything of some occurrence. So mostly chances. So like in weather, it can be will it rain tomorrow. So what are the chances of the rain? 70% chance. So this 70% chance is probability. Traffic is also, it can be regression, continuous value. It can be a classification problem as well. Traffic, will I be late for work? And it can depend on different aspects as well. um, the world is full of things we can't predict with certainty. Probability is our tool for reasoning about uncertainty. So probability in simple terms is a number between 0 to 1 that measures how likely something is to happen. So 0 is basically it's impossible, and 1 is very certain that it is going to happen, like the facts. So 1 plus 1 is always going to be true. So that is very certain. There are no chances in it. So yeah, and 90% is like very likely. It might happen. There are chances of not happening as well. So that's why 50% is equal chance. Landing, fair coin landing heads. Very unlikely is winning the lottery. Example is winning the lottery. So yeah. So why does deep learning care about probability? Because a neural network does not give definitive answers. They give probabilistic predictions. So when you show an image to an image classifier, it doesn't say this is a cat. Instead, it says that I'm 95% or 70% confident that this is a cat, and there's a 3% chance it's a dog, 2% chance it's something else. So these percentages are probability, and the entire output of the classification neural network is probability distribution over possible classes. So one of the example is this, yeah, that so, this is the neural network's output, that it is sure that 80% confident that it's a cat, 8% is a dog, then bird, fish, and others. So, and when you sum these percentage, you will get one value or 100%, because that is the probability distribution. It has to be between 0 to 1. So yeah. mm, so so this is also what softmax function does in neural network. It takes the raw numbers and converts them into probabilities that sum to 1. So two ways to think about probabilities. There are two possible philosophical interpretation of probability, and both are equally useful. First is frequentist view. So it's basically, if I flip this coin many times, what fraction will be heads? So the probability is the limit of number of times the event happened upon by total trials. And the another is Bayesian view. It's a degree of belief. Given what I know, how confident am I that this will happen? So the probability like in knife ways also we use this. The probability represent our uncertainty, which can be updated as we get new information. So in deep learning, we use both. Training uses frequentist ideas, repeat over many examples, and the prediction uses Bayesian ideas. And it expresses in confidence in predictions. So yeah, let's build a intuition. So we'll randomly flip a coin and check whether it's a what is the probability of it. Excuse me, of uh, So we're doing 5 experiments, and uh, we are in each experiment we are flipping the coin 1,000 times, and then we will look at its distribution. So initially the number of flips versus proportion of heads. So initially it was the variance was really high, but as we increase the number of, the variance converged to 50%. So like in so this is the law of large number. The proportion converges to 2 probability. So because in the first go, if I have to test it once only and I get heads, so the probability is that it always be head. Not the probability, but yeah, it shows the sample that no, it will be heads always if I take only one sample size. But as I increase it, I will eventually go to the true probability. So here initially it was only heads or tails, heads, only heads. But then as the number of samples increased, it converged to its true probability, which is 0.5, because mathematically also we know that there are only two possibilities, either head or tails. So yeah, so this is the experiment for that. Yeah, now let's see what did we learn. Excuse me. Early on the flips, if you flip early on, the proportion is highly variable. After 10 flips, you might have 70% head or 30% head. As we flip more, the proportion stabilizes and approaches the true probability, as I mentioned earlier. The law of large number, with enough trials, the observed frequency approaches the true probability. This is why we need a lots of training data with more examples. Our models learn probability become more accurate. Let's look at the summary for chapter 0. So the probability measures uncertainty. It's a number between 0 and 1. 0 is impossible to happen, so 1 is certain that it's a fact that it is going to happen. And a probability is always sum to 1. When listing all probability, 1 must happen. And two interpretations exist: frequentist and Bayesian. Frequentist is long run frequency, and Bayesian is belief or degree of belief. So neural network probabilities, its classification is fundamentally probabilistic. So yeah, let's move to the next chapter, which is language of probability. So building, yeah, let's look at some vocab terms used in probability. So first is experiment. Experiment is an action with uncertain outcomes. It's like rolling a die, flipping a coin, yeah, a possibility of having rain or not. So that action, that is experiment. Sample space is all possible outcomes that can happen. Like for rolling a die, it can get 1, 2, 3, 4, 5, 6, any of the numbers. For flipping a coin, it can be true or false. Then we have event. Event is a specific outcome or a set of outcome. Like this is the one which we want to look at. So for our experiment, it can be rolling a die and flipping a coin. But let's say I just want to look at rolling, like getting a number 6 on my die. So it doesn't matter if what the coin says. So that is event. It's a specific outcome. Yeah, let me. Yeah, it is showing the. This is the sample space. Sample space is all the possible outcomes. Event is, let's say the event is roll a 6, so only 6 should pop up. Roll an even number is these 3, like that. Now calculating simple probabilities for a fair die or any situation where all outcomes are equally likely. Event P equals to number of outcomes in an event divided by total outcomes in the sample space. So let's say if you have I want to see probability of rolling 6, it will be the number of outcomes in event. So it was 1. Like only 1 times 6 is appearing, right? So 1 divided by total outcomes in sample space. Total outcome were 6. So 1 by 6. So 1 by 6 is the probability of rolling a 6. So this is a classical definition of probability, and it works when we can list all possible outcomes and all outcomes are equally likely. A more complex example is 2 dices. Let's roll 2 dices and ask what's the probability of getting sum of 7. So first we need to understand the sample space. So this is how the sample space will look. Probability of getting these are the output of dice 1, dice 2, and these are the outcomes of die 1. Now if I get 1 here, 1 in this die, 1 in this die, the sum is 7, right? Sorry, the sum is 2. And if I get 2 here, 1 here, because 0 will never happen because we have to roll 2 dice together, both the dice together. So this is the sample space which we got. Now our event was to get the sum should be 7. So these are my events. So 1, 2, 3, 4, 5, 6. 6 is my numerator, and these are 6 by 6 sample space. So 6 by 6 is 36. So 6 divided by 36 is my probability of getting sum, which is 0.17, like that. So why it matters in deep learning? In deep learning, our sample space is often the set of all possible classes. So image classification can be particular class. Sentiment analysis is positive, negative, neutral. Next word prediction is any word from the vocabulary. So neural network assigns a probability to each possible outcome. So the types of events, it's a simple event is a single outcome. Compound event has multiple outcomes can be there, like rolling an even number. So it can be 2, 4, 6, right? So there are multiple outcomes. Complementary is everything not in the event. So like complementary, not rolling 6, which is 1, 2, 5. Mutually exclusive, yeah, that's important. Events that can't happen, that can't happen together, like rolling 2 and rolling 5. It's impossible. And independent events are one doesn't affect the other. So two separate coin flips. They are not dependent on each other. They are working on their own. So that is so the complement rule is probability of event A plus probability of not happening event A is plus when we add the both, the probability it's always 1. So let's say for example roll a dice is our event, so the probability is 1 by 6. Complement of that is not roller 6, so which can be 1, 2, 3, 4, 5. So 5 by 6. When we sum this, it will always be 1. Yeah, so that is the complementary rule, and these are some notations. So P of A is probability of event A. We'll write it like this: P of heads or P of 6, rolling a 6 like that. P A dash is the complementary thing. It's not a event like that. And then we have P and A, like both A and B can happen. So we use this inverted U for that. And P or B is AUB. So both A or B, both either A can happen or B or both, like that. And this is A A and this B. This is when probability of A given B has happened. So it is dependent on B. So what is like this? What is the probability of getting the test given the probability of a test of disease given this test is positive, like that. Uh, so these are dependent probabilities. Now let's move to the next chapter. Yeah, we have looked at the. Okay, this is summary. Now basic probability rules. Yeah, so addition rule and multiplication. So let's see how we can combine probabilities. The addition rule is what's the chance of A or B. So let's say you're playing a card game and need to draw either a heart or a king to win. So what's your probability of winning? So what you do is you calculate separate probabilities. Getting a heart is 13 by 52. Getting a king is 4 by 52. Now when we cannot just add them and get the probabilities. That is not how it will work here. The addition rule says the probability of A or B will be probability of individual A, individual B minus both of them happening together, A and B at the same time. So this is the addition rule. We will see the diagram here. Yes. So why did we do that? Minus, we'll see. Excuse me. So the red is probability of getting hearts, blue is getting kings. So we got 13 hearts and 4 kings, but one of the king is of hearts, so there's a clash, right? So like it can be a um, double calculation kind of thing will happen over here. So that's why we have to minus this extra thing. So that is why the probability of heart or king will become 13 by 52 plus which is P of heart, P of king minus P heart and king. So when we do that, we get the probability as 30%, 30.8%. Now let's look at a mutually exclusive event. If event A and B can't happen at the same time, mutually exclusive, then P and A will always be 0 because both cannot happen together. So in this case, we can just do the addition because doing minus 0 doesn't make any sense. So yeah, what is the probability of rolling a 2 or a 5? So here 2 and 5 cannot happen together, so we don't have to do that minus A and B. So we just add the probabilities and we get the value. Now what's the chance of A and B? Multiplication rule is what's the chance of A and B. So if you flip a coin and roll a die, what is the probability of getting heads and rolling a 6? So these are independent variable. Doesn't matter like if flipping a coin is not related to rolling a die. So here comes multiplication rules for independent events. So probability of A and B happening together is just individual probability of A multiplied by individual probability of B, event B. Let's see the diagram. Yes. So probability of having heads and tails is 50-50%. Now after that we have to flip a coin and we want to get 6. So probability of this is 0.5 and this is 1 by 6. So it will be around 8%, 8.3%. So deep learning connection, let's see, independent features. So in the naive Bayes classifier, we assume features are independent. So P of word 1 great and movie this is after positive review. Excuse me. is this and can be, changed with multiplication, and great after positive and movie after positive. So the naive independence assumption makes computation tractable, and even though it's not perfectly true in reality. But yeah, so let's revise the rules. So addition rule says, which is a of b plus a of probability of a, probability of b minus probability of a and b happening together. A or b mutually, when they are mutually exclusive, then simple addition rule is applied. When a and b, when they are independent, we just multiply both the individual probabilities. And when a and b, the complement rule is 1 minus p of a equals to the complementary value. Yeah. Yes. Then we have conditional probabilities. Okay, what is the probability of a given that b has happened? Excuse me. So imagine you're planning a picnic. Let's think about rain. Without any information, rain tomorrow is 30% base rate for your city. Seeing dark clouds right now, rain tomorrow, but dark clouds today. The chances are increased, right? So 70%. Checking weather radar, rain tomorrow and storm system approaching. Then the probability increases. Can you see how the probability is changing based on the previous conditions? So yeah, that is what conditional probability is. So the probability basically changes as we get more information. Yeah. So when a neural network classifies an image, it's computing, a probability of a cat given the pixel. What is the probability? This is a cat given these specific pixels. So the entire job of classifier is to compute conditional probabilities. So intuitive example, let's build. Yeah, so a standard deck of 52 cards. What is the probability of king? Which is 4 by 52, which is 7%. What is the probability of king? And the card is a face card. So there are only, 12 cards in total, 12 face cards and 4. So now can you see the probability changed to 33%. So knowing the card is face card dramatically increases the probability is a king. Yeah, it's just showing that these are the face cards and there are only 4 kings, and when you have to draw from it, the probability increases. Yeah. So the definition, so a probability of a given b had happened is probability of a and b happening to probability oopsie probability of a and b happening together divided by probability of b. So in word, the probability of a given b equals the probability of both happening divided by the probability of b. So why does this make sense? P of a and b counts outcome where both occur together, and this is p of b is a new smaller sample space. We know because we know b had happened. So we are finding the fraction of b outcomes are also a outcomes. Then this is also another example. Then let's move to the Bayes theorem. Yes, so important equation in probability. Bayes theorem in simple equation with profound implications. It tells us how to update our beliefs when we get new evidence. So we often know evidence plus hypothesis, but want hypothesis by evidence. So we know that positive test given a disease is 95%. This is what test manufacturers tells us. But we want probability of disease given the test came positive. This is what the patient care about. So these are not the same things. Bayes' theorem connects them. So P of A and A slash B is B likelihood of B likelihood of B if A is true multiplied by believed what we believe before seeing evidence divided by how likely is the evidence overall. So yeah, in words, posterior, which you want to see, is the likelihood multiplied by prior divided by evidence. So yeah, you know, think of Bayes' theorem as a belief updates machine. Start with a prior belief. I think there's 1% chance that I have disease. Now observe evidence. I tested positive. So this is probability of B. Now update your belief based on based of A based B had happened. So now think there is 16%. Earlier it was 1%, but now that I have tested positive, I think there's 60% chance that I have the disease. This theorem exactly tells you how to update your belief. So, excuse me. So, prior disease was 1%. Likelihood was 95%. And healthy was 5%. So, the likelihood multiplied by probability of disease plus healthy divided by the probability of healthy, which is 99%, minus this 1, this 1 minus this 1. So we got the probability. Now the posterior P is disease, probability of getting a disease given the test came positive is 16%. So yeah, let's see the probability. So earlier it was 1% and no disease was 99%. But as we got the evidence, which was the test result, which came to be true, positive. So now the chances of disease increased and no disease decreased. So this is how the Bayesian theorem helps you update the weights based on evidence. Yeah, this is also when the test is positive, you can see the probability of getting disease increasing. But when the test came negative, it increased to 98%, then it decreased to 78%. And when again the test came positive, it again increased. So yeah, positive test increases belief and negative test decreases it. So Bayesian theorem, yeah, in the naive-Bayes classifier, it directly applies Bayesian to classify. Bayesian neural networks treats weights as probability distributions and variational encoders. Variational encoders also use Bayesian inference for latent variables. And for understanding training, we can view training as Bayesian inference. So yeah, what are the parameters given the data? is proportional to data based on parameters multiplied by parameters. So this is the prior probability independent of the data, and this is the likelihood, what how well the model explains the data, and that gives you what we believe after training. Then we have random variables. So in excuse me. So we talked about the events like rolling a six and testing positive, but often we want to work with numerical outcomes. So this is where the random variables come in. A random variable is simply a variable whose value is determined by a random process. So x can be the number showing when you roll a die. Y can be the height of randomly selected person. Z is the number of heads in a 10 flip coin. So we use this xyz for random variables and lowercase xyz for their specific values. So now there are two types of random variables: discrete that can only take specific value and very countable values, like rolling die labeled uh, word tokens, like that. The values are basically specifics. Excuse me. Uh-huh. Alright. But continuous values, it can take any value in a range. So height, weight, 0.7728, like it can be in a range, which is a regression problem. So that is there. Let me go to the next chapter. I am not able to find the distributions. Yeah, but that is pretty much it. Random variable, so it can be Bernoulli's. Let me just so okay, let me just do this. So Bernoulli's it's a discrete type of uh, distribution. So it's mostly binary. So its value again ranges from 0 to 1, like our sigmoid. And categorical is again discrete. It is multi-class. So it can be cat, dog, elephant, like that. So multiple. And then we have Gaussian. Gaussian is the one, the discrete, the continuous value, where we can have values in any range, and we use it in weight initialization regressions and variational encoder autoencoders, like that. Thank you.